Hey there, and welcome. Today we're diving into the hidden world of molecules with a really cool technique called infrared spectroscopy. We're going to see how chemists can basically identify what something is just by watching how it does this kind of molecular dance.
You know, when we look at the world, we see all these amazing colors, right? But that's just a tiny, tiny sliver of the whole picture. The light we can actually see is just one narrow little band in this huge thing called the electromagnetic spectrum. So what if we could use all that invisible light, like infrared, to see things our eyes can't, like the very structure of a molecule? Well, that's the whole idea behind spectroscopy.
So, let's start by exploring a part of the spectrum that's just past the red light we can see. We'll call it the unseen rainbow.
That's exactly where infrared, or IR, spectroscopy comes into play. It's this amazing analytical technique that uses energy from infrared light to get a look at how molecules are built. You can think of it like putting on a pair of special goggles that lets chemists see exactly what atoms are in a molecule and how they're all connected.
Okay, so how does shining invisible light on a molecule actually tell us anything? Well, it all comes down to how molecules react to that energy, which brings us to our next section, when molecules vibrate.
To really get this, you kind of have to change the way you picture a molecule. Forget those stiff ball and stick models from your old chemistry textbook. For what we're talking about, you need to imagine that the chemical bonds holding atoms together aren't rigid sticks at all, but are actually like tiny, flexible springs. And because those bonds are like springs, they are always moving, they're constantly in motion. We call this a molecular vibration. It's where the atoms in a molecule are just jiggling and moving back and forth. They can stretch apart and then squeeze back together, or they can bend, kind of changing the angle between them. Seriously, every single molecule is doing this little microscopic dance all the time. Now here is the crucial part. A molecule won't absorb just any old infrared light you shine on it. Nope. It only absorbs energy when the frequency of that light perfectly matches the bond's own natural rhythm, its own frequency of vibration. It's a classic case of resonance. Think about pushing someone on a swing, right? If you push at just the right moment, at that resonant frequency, they go higher and higher. It's the same idea here. If the light's frequency matches the bond's vibration, the bond soaks up that energy and starts vibrating even more. But there's a little catch. Just matching the frequency isn't quite enough. There's one more really important rule that decides if we can even see that vibration happen. So let's take a look at the dipole dance rule. Okay. Here it is. This is the golden rule of IR spectroscopy. For a molecule to actually absorb that IR radiation so we can see a signal, two things have to happen. First, the vibration's frequency has to match the light's frequency. That's the resonance we just talked about. But second, and this is so important, that vibration has to cause a change in the molecule's overall electric charge balance, what we call its net dipole moment.
This does a great job of showing what that means. Let's use carbon dioxide, CO2, as our example. So in this first motion, you've got what's called a symmetrical stretch. The two oxygen atoms are moving away from the carbon in the middle at the exact same time, and then back in, perfectly in sync. Because it's so symmetrical, the individual charges cancel each other out completely. The net dipole moment for the whole molecule stays at zero the whole time. Since there's no change, that vibration is IR inactive. Our machine just can't see it. But now, check out the second motion, the asymmetrical stretch. Here, one oxygen moves in while the other moves out. This totally breaks the symmetry. The charge isn't balanced anymore, and it's constantly changing as the atoms move. Because that net dipole moment is changing, this vibration is IR active. It absorbs that specific frequency of light, and we get a signal.
So let's just break that down one more time to be super clear. An IR inactive vibration means no change in the net dipole moment. For that specific dance move, the molecule is basically invisible to our instrument. But an IR active vibration is one that does cause a change in that dipole moment. The molecule absorbs the energy, and bingo, a signal is detected and shows up on our graph. All right, so we've zapped our sample with a bunch of infrared frequencies, and our detector has kept track of which ones got absorbed. So what's the result? Well, we get a molecular fingerprint, which we're about to learn how to read. The output is something called an IR spectrum. It's basically a graph that shows us exactly which frequencies of light were absorbed and how much. And what's just incredible about this is that the pattern of peaks and valleys on this graph is totally unique to each molecule. That's why we call it a molecular fingerprint. Just like human fingerprints, no two different compounds will ever have the exact same IR spectrum. You can imagine how useful this is in forensics for identifying some unknown substance.
Now, chemists have a system for reading this fingerprint. They split the spectrum into two main zones. Over on the left, at the higher energy range, from about 4,000 down to 1,500 wave numbers, which is just a unit for frequency that chemists like to use, we have the group frequency region. The peaks you see here are like big flags, telling you if certain functional groups are there, like a C double bond O or an OH group. Then, on the right side, from 1,500 down, you've got the famous fingerprint region. This part is way more complex. It's got tons of peaks that come from vibrations of the entire molecular skeleton. And while it's tough to figure out what every single peak is, the overall pattern is absolutely 100% unique to that molecule. This is how we can confirm the identity of something by matching it to a known sample.
So let's bring all this together now and really see why IR spectroscopy is such a powerful tool for chemists.
So to sum it all up, an IR spectrum gives us a few critical pieces of the puzzle. It tells us which important functional groups are there or which ones aren't. It gives us that one-of-a-kind molecular fingerprint to nail down a compound's identity. And it gives us clues about all the different pieces that make up the whole structure.
Of course, like any technique, it's not perfect. The advantages are huge, for sure. You can analyze solids, liquids, or gases. It's super fast and pretty easy to do. You only need a teeny tiny amount of your sample, and the instruments aren't crazy expensive. But it has its limits. It's not going to work on single atoms like helium or on what we call homonuclear molecules. You know, molecules made of only one type of element, like the oxygen and nitrogen that are all around us in the air. Why? Well, their vibrations don't cause a change in dipole moment, so they're completely IR inactive. It also works best on really pure stuff. Trying to read the overlapping fingerprints in a big, messy mixture can be a real headache.
So IR spectroscopy lets us listen in on this silent, invisible dance that molecules are doing all the time. Every single molecule vibrates with its own unique signature, a fingerprint that tells us its story, its identity. And that really just leaves us with a final question. As we get better and better at understanding this language of vibrations, what other secrets are just waiting to be uncovered in this molecular dance?